Hey guys, this is Karan. I live in Saudi Arabia. I study in 9th grade in Yammer International School. Today, we will be talking about inelastic and elastic collisions. So what we are going to do is expand our knowledge with collisions in physics. Okay, how the collision was related in physics, which I taught you before in my videos. Okay, so I'm not going to explain that again. And today we are going to expand the knowledge. Also, we'll be talking about special types of collisions, where collision has an angle, okay? So it involves some kind of angle that's thrown at or being thrown at, okay? Now before we go on to the equations, I want you guys to know the momentum is being conserved, okay? In this lecture or in this tutorial, the momentum is always going to be conserved, and there's the reason why Newton's law is so much famous around the world. Okay, so like I told you before in my previous section that P F is equal to PO. Okay, it's equal to PO. In this way, some of the collision as in inelastic and elastic collisions perfect. So I'm going to tell you what we are going to talk about here. So today we will be talking about elastic collisions, inelastic collisions, perfectly collisions, now glazing collisions. Okay, but also remember that in this topic we will be either this inelastic has conserved of momentum or conserved of kinetic energy. Okay. So let's begin our topic with elastic collisions. Okay. Now elastic. Okay. So like I told you before that the momentum or the kinetic energy has to be conserved in this type of collisions that we are going to be talking about. Okay, in elastic collisions, momentum, which is represented as P, and kinetic energy are both conserved. All it conserved means that it's constant. Okay, it's not changing its speed. Okay, for example, if you were to pick an example, it would be billiards. Okay, it doesn't change its shape. Okay, so if you were to have if you have playing this game, what you do is when you hit one ball to another ball, what happens is it just hits the ball. It's conserved energy. Okay, either kinetic energy is conserved or momentum is conserved, but in this case both momentum and kinetic energy is conserved. Okay, now how would you represent that in equations? Okay, it's really simple. Okay, we know what's the formula for P. Well, mass times velocity is P, but remember we'll be talking about two things at a time. So mass 1 times velocity, which is initial. Okay, and then we have momentum. Okay, so plus m2 times vi. Okay, mass 1 and its initial speed plus mass 2 and mass 2's initial speed is equal to mass 1, okay, mass 1 times final velocity, okay, plus mass 2 Okay, let me just write it down here because I'm running out of space. So this is equal to mass 2 times final velocity plus mass 1 times final velocity. Okay, it's really simple. Okay, what we do is we have two objects we're comparing two objects. So what we do here is we have mass 1 of the object, we have mass 2. You have to find the initial speed of velocity, which is initial velocity, and you have final velocity, and there is again mass 1 and mass 2 of it. Okay, now all this is it's conserved. That is why we put equal sign over here. Okay, that means it's a conserved momentum. Now what about kinetic energy? Because elastic collision has kinetic energy to be conserved as well. So kinetic energy, as I taught you in my previous tutorials on physics, is half and mass 1 times velocity 1 squared, okay, plus half mass 2 times velocity, which is second velocity, to be squared, is equal to, okay, half mass 2 times velocity, which is final. Okay, let me just write initial, okay, which is being squared, plus, and I'm going to be writing down over here, which is half times mass 1 times final velocity being squared. And as you guys have noticed, it has an equal sign as well. That means momentum we just talked about is conserved, and kinetic energy is also conserved by this equation over here. Okay, now let's compare this with inelastic collision. Okay. And inelastic collision should have either kinetic energy to be conserved, or it should have momentum to be conserved. So we're just gonna find out what is conserved right now. So we'll be talking about inelastic, and in inelastic collision, what is conserved is the momentum. P is conserved. Okay? So kinetic energy is not conserved, so we can't say, like we said before, that half mv square is equal and big equation. We can't put equals, okay, in between, because it's not conserved. Well, we can put the momentum equations, what we wrote ahead before, okay, a moment ago. We can put it with this equation. So that's inelastic collision over here. Now what is perfectly inelastic collision? Okay, now to explain this term, okay, if you were to have take a Play-Doh, okay, Play-Doh, and you throw it, and if you have two Play-Dohs, okay, if you were to, let's take two gummy substance which sticks to each other, okay, like suppose a magnet, okay, what happens is when you have two magnets in your hand, and when you throw it, it sticks to each other, okay, and it sticks to each other and falls down together. They don't fall apart and fall down. So when it sticks each other, it's perfectly inelastic collision. That's basically it. And I'm just gonna erase this because in perfectly inelastic collision, only momentum is being conserved. Okay. okay, in perfectly inelastic collision. So we can say that, but what happens is the equation changes because they're stuck to each other. Now, the equation which I showed you a moment ago, okay, was for elastic, okay, it was for elastic. Now it's the same equation, but what changes is the variables, okay. So let's go ahead and let's see what changes. So we said mass 1 times initial velocity, okay, and this is the equation for momentum, mass times velocity, and then we put mass plus mass 2 times initial velocity of mass 2. But what happens is when they were thrown, they stick to each other. So we just do mass 1 plus mass 2 and their final velocity. So this becomes the equation for perfectly inelastic collisions. Because we add these two masses over here, because if you were to have two magnets, okay, and they were thrown at something, but when they stick to each other, and when they fall, like for example when they fall, they don't go apart, do they? No. So what happens is the mass of this tiny magnet plus the mass of this big magnet adds up together and they fall down with the same speed, okay, because they are stuck to each other. Okay, that's basically perfectly inelastic collision, and only kinetic energy is not conserved. Okay, so we can't put half mv squared. Okay, we can't use that equation because kinetic energy is not conserved, only the momentum is conserved. Okay, now let's go back and review what I just said. Okay, so let me go back. Okay, I'm gonna leave this up here. Now, let's go back, and we talked about three things, right? Perfectly inelastic, which is only P is conserved. Okay, and then we first talked about elastic, okay, in which only P and Ke is conserved. Okay, now we talked about inelastic, in which only P is conserved, like in perfectly inelastic. And you can see that is why inelastic and inelastic has both P is conserved in it. Okay, but what's the difference over here? That it doesn't get stuck. Okay, in this perfectly inelastic collision, the two objects that we are using, okay, for example Play-Doh, when you throw it up first and it gets stuck to each other, okay, it gets stuck and fall down with having to each other, so it gets attracted and stuck by each other and falls down together. In this it doesn't. That's the reason why we put just P is conserved, and the formula is you can equals the same thing we write over here, just we change the final velocity. Okay, we just change it to final. Now let's talk about one more collision, and these are all collisions you guys can see. Okay, now this over here is called glancing collision. Okay, glancing, glazing. Okay, now what is being conserved here? But before me telling you what is conserved here, let me draw a diagram and show you what it is first. Okay, so if you were to have a ball right here, okay, and it's going with some velocity, okay. So if we were to have a ball right here, what happens is it's going at some velocity, okay, and when it hits the ball, not all the force of the ball which is applied over here hits the ball. It attracts some energy, okay, some force is being applied to this ball to move the ball, okay, and this ball loses that much energy, okay. So, and again, this is by an angle, so we use sine, okay, because you guys can see. So if this was a ball right here, and it goes with some angle, okay, and this is angle, and this was the ball right here, and it goes this direction, it has some angle as well, okay. So these two balls have some angle that they're moving, okay. Let me do this with black. Some angle, okay. Now it's important that you have to you can have elastic and inelastic over here. Let's talk about its momentum. Well, momentum is being conserved, okay. It's being conserved because initial is equal to final momentum, okay, and the direction applies to the momentum formula. So the kinetic energy isn't conserved because only some amount of force is acting onto this ball, so we can save, okay, by just looking at it, because this, it has some more speed than this ball and it has more mass than this ball, so kinetic energy isn't going to be conserved. Only that the thing's gonna be conserved is the momentum, okay. So but we have x direction over here, which is going vertical, and this is going horizontal, so we have x direction over here. This is going vertical as well, and this is going vertical as well, so we have both x directions that we will be moving on. So as we apply the momentum formula, I'm just going to erase this part over here. As we just use the momentum formula, we put initial of momentum, which is x direction, okay, and then you multiply with y of x, because it's going to the y coordinate as well, and we have p o times y, okay, and p o y. Okay, we have initial momentum of x and y over here. That is the reason why we put like this, and this over here is in the equation, so don't worry about it. I just wrote it for you guys to understand. This is going to x and this is going to y, okay. Okay, and this is called glazing collision over here. So to understand this concept, you have to work the problems out, okay. So let's get started with the problems, okay. Now let me just go ahead and erase the board so you guys can see the cushion. So the question goes like this. A skateboard has mass of 1.2 kg, is rolling at the speed of 6 meters per second, okay, and suddenly a dead bird which has a mass of 0.4 kg falls down from the sky. What is the speed after the bird lands? Okay, so here we're going to be consider a perfectly inelastic collision because the bird is getting stuck on the skateboard. Okay, so we know that in perfectly inelastic collision, momentum is being conserved. Okay, so we know that momentum of a bird plus velocity of the bird, okay, is equal to plus momentum of the skateboard plus velocity of the skateboard is equal to, we add these two masses over here, which is mass of a bird plus mass of skateboard times their final velocity. Okay, now we just replace these values. What is the mass of the bird? Well, we know the mass of the bird is 0.4 kg, and we actually multiply here. Okay, because mass times velocity is what we get momentum. Okay, so we have 0.4 and we multiply by, they haven't given us, this is when we have to analyze the values in each variable. Since they haven't given it, we just put it at 0 over here, plus mass of the skateboard, they have given us to be 1.4. okay, and the velocity was going, okay, it was the velocity it was going was 6 meters per second. Okay, now what we do over here is add 0.4 plus 1.4, okay, and their final velocity, which we are trying to find out. So this is easy over here because any number multiplied by 0 is 0 as well. So I'm not 0. Okay, now what is 1.4 times 6? Well, if you were to do that in calculator, 1.4 times 6, you would get 8.4. Okay, now you would be getting, remember the plus sign in the middle, 8.4. okay, now it's equal to 0.4 plus 1.4, okay, it's 1.8 times their final velocity, which we don't know. Okay, now you add over here, 8.4 plus 0 is 8.4 is equal to 1.8 times final velocity. And since we reached over here, now some of you might just divide 8.4 by 1.8. That is correct to find the final velocity, but you have to understand the equation that is being formed over here. And again, this is perfectly inelastic collision because the dead bird is getting stuck on the skateboard. Okay, it's falling on the skateboard, so it's going to remain on the skateboard as well. So when you divide 8.4 divided by 1.8, you should be getting 4. The final velocity is equal to 4.6667, and that is meter per second because velocity is meter per second. And again, this problems just takes practice, so I would like you to rate, comment, subscribe, and thanks for watching. Also, if you want more practice on this, okay, you know what you do is just change the values and keep on doing it again and again till you get a hang of it. Thank you for watching.